Hello, let's study again together. This time we work on section 13.3 on the arc length and then curve reparameterization, unit tangent, unit normal, and curvature. Okay, let's start doing this. You will see most of them here is actually applying formulas, and it tends to be procedural. Okay, for example, let's see number 2. We have RT equals to 2t t squared 1/3 t cubed for t between 0 and 1. We want to find the length of the curve, so we do the first derivative first. And then get the magnitude. But this is equals to the square root of t squared plus 2 being squared. So this is supposed to be absolute of t squared plus 2, but t squared plus 2 is positive anyway. So we can safely just simplify this way, and the arc length from 1 to 2, I'm sorry, 0 to 1. The arc length from 0 to 1 will be integral from 0 to 1 of t squared plus 2 dt, which is 1/3 t cubed plus 2t from 0 to 1. Oh, it's polynomial. So from 0 to 1 is basically adding the coefficients, right? That's for number 2. And then let's go on. Let's see number 4. Of course, you don't expect number 2 to be hard, right? But at the same time, you don't think that all this section will be just that simple. I think what makes it seems to be easier is the fact that the curve is managed by polynomial in number 2. But then as we go on further, you can see here we get something else, like we have trigonometric, and in this case we have log of trig, where the t is from 0 to pi over 4. This is just another way to write the interval. Okay, so r prime t will be negative sine t, cosine t, and negative tangent t, whose magnitude is square root of negative sine t squared plus cosine t squared t plus negative tangent t squared, which will give us square root of 1 plus tangent squared t, which is square root of secant squared is absolute of secant t. Now, however, in that interval, in this interval here, secant t is positive, right? It's in quadrant 1. Okay, so the arc length from 0 to pi over 4 will be integral from 0 to pi over 4 of secant t dt, which is natural log. I do expect you to memorize this though. Integral of secant t, natural log of secant t plus tangent t from 0 to pi over 4, which is natural log of secant pi over 4 is radical 2, tangent pi over 4 is 1, minus natural log of, at 0 this is 1, this is 0, natural log of 1 is 0, So we are left with natural log of square root of 2 plus 1. That's for number 4. Let's see number 6. RT is 12t, 8t to the 3 halves, and then 3t squared, 4t from 0 to 1. Okay, so R prime t, that's 12t, 12t to the 1 half, and then 6t. You know what? I can factor the 6 out. So this is 2t to the 1 half, and then t. So the magnitude of R prime t will be 6 times square root of 4 plus 4t plus t squared. Gada boom, that will be 6 absolute of t plus 2. Again, but in that t between 0 to 1, we can safely say that this is 6 times t plus 2, right? Just remember when you apply square root of something squared, it is not that thing, but it's supposed to be absolute, and you can just take away the absolute only when you guarantee the guy inside the absolute is non-negative. Okay, that's something we learned in pre-calculus though. Now then come back here. So the arc length from 0 to 1 will be integral from 0 to 1 of 6 times t plus 2 dt, which is 6 times 3 minus 2, huh? Right? What am I doing? 1 half t squared plus 2t from 0 to 1. Oh, yeah, we just apply adding the coefficients. 1 half plus 2, 5 halves, so that's 15, huh? Okay, that's for number 6. Let's go on. Reparameterize the curve with respect to the arc length measured from the point t equals to 0. Let's see number 14. Number 14, we have rt equals to e to the 2t cosine 2t. Ooh, this is ugly, huh? 2 e to the 2t sine 2t. So the r prime t will be 2e to the 2t cosine 2t minus 2e to the 2t sine 2t, comma 0, comma 2e to the 2t sine 2t plus 2e to the 2t cosine 2t, which I can factor 2e to the 2t, right? I get cosine 2t minus sine t, comma 0, comma sine 2t plus cosine 2t. By the way, if you notice, because the y component is constant, then this curve is actually part of the plane y equals to 2. Okay. In other words, if you try to visualize that, let's say this is the plane y equals to 2, the curve is actually moving on that. Okay, on that plane. Now, then the magnitude, therefore, will be the magnitude of e. I suppose to use this absolute of e, 2e to the 2t, and then square root of cosine 2t minus sine 2t squared plus sine 2t plus cosine 2t squared. Okay, what I want to say is like absolute of exponential is, well, exponential function is always non-negative, right? So we actually don't need absolute sign there. But for now, let's put it first. And then the next step, we realize, oh, you know what? I don't need that absolute sign, right? And then the guy inside here, I hope you realize this is equals to 2. I wonder if you can see it. Okay, try to work it out. Try to work it out. You will see that's equals to 2. So the arc length, no, sorry. The arc length function from t equals to 0 to t will be integral from 0 to t of 2e to the 2u square root of 2 du. Okay, which will give us square root of 2e to the 2u from 0 to t. Is it right? Which, if I plug in t, I will get square root of 2 of e to the 2t minus 1. Now, so when we reverse that, we want to have t as a function of s. That will be s over square root of 2 plus 1. And then, you know what this is? Let me do it a bit slower. This is e to the 2t, such that t will be 1/2 natural log of s over square root of 2 plus 1. Okay, actually I don't need a t, huh? I just need 2t. Well, anyway, let me change it to 2t. Well, why I say that? Because I have 2t here. In fact, I have e to the 2t and I have 2t, right? Those are the things that I will need to substitute. Okay, so e to the 2t is, so r instead of, yeah, r t as a function of s will be s over square root of 2 plus 1 cosine of natural log of s over square root of 2 plus 1 comma 2 comma s over square root of 2 plus 1 cos, I think it should be said sine of natural log of s over square root of 2 plus 1. Okay, now that's the curve reparameterization. Let me move this below that and then make it a bit smaller. Okay, I think that's good enough. And then let's go on to the next question. Find the unit tangent factor and then unit normal factor, and then find the curvature. Number 18. Okay, RT is t squared sine t minus t cosine t cosine t plus t sine t for positive t. So the r prime t will be 2t cosine t minus cosine t minus plus actually t sine t, and then negative sine t plus sine t plus t cosine t, which simplifies to be 2t, t sine t, and t cosine t. Remember, the unit tangent factor is defined to be the r prime t divided by its own magnitude, right? Okay, so the next thing I will do is to find the magnitude of that r prime t, which will be square root of 4t squared plus t squared sine squared t plus t squared cosine squared t. If I factor the t squared out, I'll get square root of 4 plus sine squared plus cosine squared, which is 1. Okay, or but because the t is non-negative, t is positive, I can safely omit the absolute sign. So I get t square root of 5. Therefore, the unit tangent factor at time t will be, that's 2t, t sine t, t cosine t over t square root of 5. Okay, which is equal to 2 over square root of 5 sine t over square root of 5 cosine t over square root of 5. Now, by the way, actually, if you notice that we have common factor t there, right? If you have common factor t there, just get rid of that t, so you have this right away, and then divide it by the length of this factor, which is square root of 4 plus 1, right? If you think about it, okay? If you think about it. Now, that's the nice thing about finding unit factor. Not only unit tangent factor, you will see for unit normal factor is the same, and unit binomial factor also the same. Basically, if you have common factor, let's say a times b comma c comma d, let's say that's the factor v, then the unit factor of that factor v will be, just take the bcd and then divide it by its own length, but by that length. What happened to the a terms? Well, because that's common factor, you will see that common factor a here later on will be divided by common factor a. Okay. Now that's actually you will see that's actually a very useful hint. Okay, in finding unit factor. Now let's go on with normal factor. Now normal factor is defined to be, unit normal factor is defined to be unit tangent, the derivative of unit tangent factor over its own length. So let's find the derivative of unit tangent factor first. The derivative of unit tangent factor will be 0 and then cosine t over square root of 5 negative sine t over square root of 5. Notice I can factor the square root of 5 out, 1 over square root of 5 out. Okay, and the length of that factor is 1, right? Okay, so you will see that if we use this formula here, you know what, I will just show you. So the magnitude of the derivative of unit normal factor will be 1 over square root of 5 times blah, 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 1, which is 1 over square root of 5, right? So you see that the unit normal factor will then be 0, comma, cosine t, comma, negative sine t. Okay. That's the nice thing about having the common factor, right? Number 20. Number 20. RT equals to T 1/2 T squared and then T squared. The derivative is 1 T 2T. No common factor. Dang it. So absolute of R prime T will be square root of 1 plus T squared plus 4T squared. That's square root of 1 plus 5T squared. So what is the length of unit tangent factor? That's 1 over square root of 1 plus 5T squared of 1T 2T. Okay. Yeah, I keep it that way. And then how about the derivative of unit tangent factor? The derivative of unit tangent factor will be, this is to the power of negative 1/2. So I will get negative 1 over 2 square root of, actually no, not square root, that will be 1 plus 5T squared to the power of 3/2 on the denominator multiplied by 10T times 1T 2T and then plus 1 over square root of 1 plus T squared times 0, 1, 2. Notice that I basically do product rule here. I do product rule, this kind of a product rule. Suppose I have factor V as a function of T, of function times factor W. Then the derivative of this, I apply product rule F prime W plus FW prime. Okay, that's what I did up there. Okay, of course you can just multiply that in and then do the derivative one by one also, whichever you would think is easier for you to execute. Okay, I think my reflex was like, hey, you know what? I just do product rule here. Now, if we think about it further, this is actually negative 5T over 1 plus 5T squared to the power of 3/2 times 1T 2T. Okay, plus I'll multiply this guy by it should be 5T here, by 1 plus 5T squared on the top, such that the denominator has that LCD to the power 3/2, right? And then times 0, 1, 2. And then I will combine like terms. Okay, let me just do it this way. So this is 1 plus 5T squared to the power of 3/2. Okay, and then inside I will get negative 5T. The second term will be negative 5T squared plus 1 plus 5T squared. And then the third term will be negative 10T squared plus 10T squared, which is equal to 1 over 1 plus 5T squared to the power of 3/2 and then negative 5T 1, 0. Okay, so what is the unit normal factor then? It will be that derivative of that unit tangent factor divided by its own length. You will see we will cancel the common denominator, okay, and dividing this by its own length. Okay, So this is equal to negative 5t 1 0 over square root of 1 plus 25 t squared. Okay. Of course, always check my computation. Okay, always check my computation, but it is technically correct. Next one, number 22. Use theorem 10 to find the curvature. I don't remember what is theorem 10, but I think the curvature, I think I will use this formula. The curvature at time t will be the magnitude of r prime t cross r double prime t divided by magnitude of r prime t cube. You can check your formula for that. I think that's the one easy to execute. Okay, that's the one easy to execute. Oh, you know what? I think the previous question they asked us to find the curvature also. You know what? Let me step back a little bit. Put some here. Okay. You know what? Let me take the whole thing here. And then shift it down a little bit so that I have enough space for this guy. The curvature at time t is defined to be one formula is magnitude of t unit tangent, the derivative of unit tangent factor divided by the magnitude of r prime t. Right? Okay. So we have 1 over square root of 5 divided by what is r prime t? T square root of 5. That will be 1 over 5t. That's the curvature. Okay, I think we have that formula also in number 20 already. Like the curvature at time of t is the magnitude of unit tangent factor, which is square root of 1 plus 25t squared over 1 plus 5t squared to the power of 3 halves, big over square root of 1 plus 5t squared, which will give us 1 plus 25t squared under square root over 1 plus 5t squared being squared. Okay, that's the curvature. Now then, if I just need to find the curvature right away, instead of find the unit tangent factors and then do the derivative, I will just play with the r prime and r double prime thingy. Okay, so for example, number 22, the rt is t squared e to the t, such that the r prime t is 1 2t e to the t, whose magnitude is square root of e to the 2t plus 4t squared plus 1. And then r double prime t will be 0 to e to the t, such that r prime t cross r double prime t give us I j k of 1 to t e to the 2t, I'm sorry, e to the t and 0 to e to the t will be 2t e to the t minus 2 e to the t negative e to the t. Why did I keep on saying e to the 2t? Should be e to the t only. And then the last part is 2. Okay, whose magnitude, let me continue here, whose magnitude equals to, oh wow, this may be ugly, huh? Square root of 2t e to the t minus 2e to the t squared plus negative e to the t squared plus 4. That will be 4t squared e to the 2t minus 4t e to the 2t plus 4 e to the 2t plus e to the 2t plus 4. Oh wow, that's really ugly, huh? Honestly, I cannot stand this. I cannot stand this. This is 4t squared e to the 2t minus 4. Actually, not 4. It should be 8, huh? It should be 8. 8t e to the 2t plus 5e to the 2t plus 4. I don't think that's factorable. I don't think that's factorable. So the best I can say for the curvature, therefore, wow, I didn't expect it to be that ugly though. Let me check my computation in case I make anything wrong. Yeah, nothing, huh? It seems to be okay. It's just become something so ugly. Okay, so I have square root of oh, there's no square there, just 8t. Divided by magnitude of r prime cube. So this will be e to the 2t plus 4t squared plus 1 to the power of 3 half. I'm sorry. Number 53. At what point of the curve, so we have RT equals to TQ 3T T to the 4th, right? Now we want the normal plane has normal plane I think I should rephrase it. At what t does the curve of this have normal plane parallel to 6x plus 6y minus 8z equals to what? But normal plane is normal to unit tangent factor, right? And this plane here is normal to 6, 6, -8, which is parallel to 3, 3, -4. So what we need to do is actually find oh, another thing, that unit tangent factor is actually parallel to the r prime t. Okay, so what we need to do is to find, so find t such that r prime t is parallel to 3, 3, 4. Okay, now actually you will see that if you play with the unit factor, then you basically need to find at what t is the unit tangent factor equals to 3, 3, -4 divided by its own length. So 18 plus 16 square root of 34. Okay, that's what we need to find. But in essence, we are actually find the derivative of RT, and when will that be multiple of that 3, 3, -4? Okay. So I think I will proceed with the first option, okay, but again, maybe seeing it this way is easier. Okay, seeing it with the unit tangent factor is easier. Okay, let's start. So the r prime t will be 3t squared 3 4t cubed. But this is basically 3, 3, -4 when t equals to -4, right? Okay, so I set this equals to 3, 3, -4, right? And you can see from the z component, 4t cubed equals to -4 implies t equals to -1. Okay, so at what point will that be? Oh, well, we find the position factor at 1. That will be, I'm sorry, at -1. There will be -1, -3, 1. Okay, so at what point? At the point, now I use coordinate, -1, -3, 1. Okay, at this coordinate, which is when t equals to -1, will the normal plane parallel to that plane? Okay, I think I need to remind you about this. Okay, normal plane is normal to unit tangent factor. Okay, and then what other plane? I forgot. The one that is normal to normal factor, tangent plane. And then the one that normal to binormal factor is osculating plane. Okay, remember this. Let's go on the next question. Oh, by the way, I think I want to say that tangent plane is also called rectifying plane. I don't know if I mentioned this before, rectifying plane. Okay, next question. Is it the last question? Yeah, one more. So number 56, show that the osculating plane at every point on the curve RT is on the same plane. What can you conclude about the curve? Now, osculating plane is normal to binomial factor, right? Okay, now, since it is on the same plane, we actually need to show, so let's say this is the curve, right? Okay, and the osculating plane is on the same plane. It means you need to show two things. First one, that the curve is on a plane. Okay, the curve is on a plane. And then second, the binormal factor, because it's already unit, must be constant, is constant factor. Okay. Of course, at each point here, the factor that is normal to that osculating plane may be different length, but when you look at the unit of that, they must be the same. Okay, so let's do it that way. Let's start with r prime t, which is t plus 2, 1 minus t, and then 1/2 t squared. What am I doing? That's rt, right? And then r prime t, therefore, 1, -1 to t. Okay, so unit tangent factor will be this guy divided by its own length, which is square root of 2 plus 4t squared. Okay. Now then, how about the unit normal factor? Unit normal factor will be negative 8t over 2 times 2 plus 4t squared to the power of 3/2, 1 -1 2t plus 0, 0, 2, which if I put things together, I will get negative 4t of 1 -1 2t plus 2 plus 4t squared 0, 0, 2. I do the LCD, by the way. I will get and then at the bottom I have 2 plus 4t squared to the power of 3/2, which will give us, for the x component, that's negative 4t. For the y component is positive 4t. And for the c component is negative 8t squared plus 4 plus 8t squared over 2 plus 4t squared to the power of 3/2. But on the numerator, you will see that the negative 8t squared cancels, right? And I can factor the 4t out. I'm sorry, this supposed to be t prime t. Okay, and the denominator is 2 plus 4t squared to the power of 3 half. Okay, but then if we try to find the unit normal factor, then you will see this is basically 1 over square root of 3 negative 1 1 1. You try it. You try it. Seems you will see again and again and again that it's basically the whole factor here divided by its own length, right? But the length must have this factor, which they end up canceling each other. So you will see we basically have only this part here divided by its own length. Okay. Now then. Let's see. So t cross n t equals to I j k of you know what, I will play with the factors, with the common factor outside. So I have 1 over square root of 2 plus 4t squared of 1 negative 1 2t, and then 1 over radical 3 negative 1 1 1. So the unit, the binomial factor at time t, why I suddenly question if it's supposed to be a constant? Because that's the statement I made earlier, right? That if the oscularity plane is the same plane, then I need to show that the unit binomial, the binomial factor should be constant, which apparently it is not. Kind of strange, huh? It's kind of strange. Anyway, so this is 1 over square root of 6 times square root of 1 plus 2t squared of negative 1 minus 2t, negative 1 minus 2t, and then 1 minus 1, 0. Which I can factor again, which I can factor again. This will be negative 1 minus 2t over square root of 6 square root of 1 plus 2t squared 1 1 0. Which is a factor of it's a function of t, I can tell, but this factor is always parallel to 1 1 0. Right? It's always parallel to that factor. Okay. You can try, if you find the length of this binomial factor, you will see that the length is 1. So it's basically, I want to say that. Yeah, I want to say that this bt here must be 1 over radical 2 of 1, 1, 0. Okay. Now then, so which plane is that? It must be parallel to, so the osculating plane, which is normal to B, right? To be honest with you, I kind of like question myself now. I don't want to say this is equal to. At least that's not what I have. At least that's not what I have. I just want to say that this is always a scalar, right? Okay. Scalar multiple of these. Does it make sense? Okay. But at the same time, it has to be unit length, because binormal is unit length. So don't you think it's supposed to be the binormal? I put a question mark here because I myself question myself right now. So this is 1, 1, 0 over square root of 2. Is it right? Okay. Yeah, I kind of like question myself. I will do one checking later on. I need to do some little checking later on. But anyway, then the oscillating plane must be parallel to x plus y equals to constant. Okay, I take it from here. I take it from there. Okay, and then what will that constant be? What I will do, I will just plug in the RT to show that all the first, the oscillating plane must be normal to this binomial factor. Okay, what I want to show is if I plug in this RT here into this plane, I will get a constant for every t. So t plus 2 plus 1 minus t equals to constant d, and d equals to 3. In other words, the osculating plane is x plus y equals to 3. Okay, and then the binormal factor is always perpendicular to this. Okay, let's confirm that with our with GeoGebra. I have that here. Okay, so we have, I forgot how to do the RT. In parentheses, t plus 2, comma, 1 minus t, comma, what is that? Let me see again. What is the z component? 1/2 t squared, comma, 0.5 t squared for parameter t. Let's make it from -2 to 5. And then the next thing I put in is that plane x plus y equals to 3. I want to show that this plane and the curve is exactly on the plane. Do you see that? Okay. I think, will this be a better view? Yeah, I think this is a better view. Let me screenshot this one. And what I want to say is that the binormal factor is always perpendicular to that plane, right? These are the binormal factor. Okay, that's for today.